It's due tomorrow. Again, it's probably a bit easier than some of the others, and it builds on the previous projects 2 and 3, putting them together, and you actually get to sort of execute a query, albeit not a query written in SQL. So you can take advantage, as you know, of our Project 3 solution. And by the way, I expect that we will be giving you I'm using the Project 3 grades later today. It's been a while. Things get tight at the end of the term. Interesting discussions. You know about the final. It covers the entire term. It's in this room on next Wednesday, a week from today, from 4 to 7 p.m. And all the material from the projects could be on the final. You get to bring in the cheat sheet as usual, just one piece of paper, two-sided. And there haven't been a lot of questions about last year's final, but I expect that will change before next Wednesday. I can try to address them. I will mention that there will be a lab section tomorrow, so Sloan is going to be there for that. Of course, the lab is due, Project 4 is due tomorrow, but on Friday, Saloni will be there. You can ask him questions about the practice midterm. You can also post things on Piazza, which I'll be glad to answer since there is no answer sheet for the practice final. Or you can just ask questions about the entire term. So, you know, office hours and lab sections continue to the end of the term. Of course, there are no office hours or lab sections next week. That's finals week. There are these things which are evaluations by students of instructors and teaching assistants that close of this coming Sunday, which is the day before finals begin. As emphasized, we don't get to see ever what an individual said. The summary of what's there does become available, but it's about a month after that closes, so that won't in any way affect the grades, and constructive responses can end up helping future courses in various ways. So let's see, where we are. There we go. So we started talking last time, we're continuing in the lecture on distributed data. And again, emphasis, this lecture, as well as the previous one on parallel, will be on the final. The next 2 lectures, we're gonna get to spatial data, probably not today, but certainly on Friday. And if we get to it, some more about LSM trees, log structured merge trees. The new stuff in those exams won't be on the final. Any old stuff we went over, of course, could be on the final. So there are 2 ways that we talked about doing replication. One way is you keep all the different copies up to date. Sometimes that's been referred to as one copy serializability. It's as if there was only one copy, even though there are multiple copies. And that, you know, in some ways is really nice. It's like serializability in general. It's really, really pretty, and it's really, really expensive. So it doesn't end up necessarily being used all the time. There is a notion of asynchronous replication, which basically says, let's say if I have 2 copies of my data, I'll send the changes that I make to my backup. I'll send them reliably so that the backup will almost certainly get the copy eventually, but it may not have it currently. And that would mean that if the backup takes over, that it may not have the same data that the primary had at the time that the primary failed. And so it may have the data as of a second ago, but it may not have the data necessarily now. And that ends up getting interesting. But there's another approach that gets used based on voting, where the idea, according to what I refer to as Thomas's rule, is that R plus W greater than N. And it's a number of sites that you have. So for example, you might have 5 sites. R is the number of sites that you have to read to ensure that you have the current value of the data. So, and W is the number of sites that you have to write to ensure that the writes are going to be visible to readers. And you don't have to necessarily update all of them immediately, although it is a good idea to keep them up to date, but you may do it a little more lazily. So for example, if N is 5, and you might have R as 3 and W as 3. And notice that the intersection, as we discussed last time, of a set of 3 and another set of 3 has to include one that received the last read and you can tell from the versions, when you read, you can tell the version of the data that's been written. Version is always something that keeps increasing. And you can tell that, you know, there might be 2 sites where they have version 78 and another site where it has version 80. And version 80 wins, even though 2 sites have version 78, because 80 is the latest. So if you write 3 and you read 3, you will always get one of the sites that have the latest. And you can also do this, for example, with 4 and 2. So you could do something where you only write 2 and you read 4. And again, if there are 5 sites, an intersection of a set of 4 and a set of 2 has to have something in common. You typically won't want to go ahead and work with 7 written and 4 read. Reads tend to be more common than writes. You may not want to have to bother reading 4. A situation in which you read any and write all, that makes it very easy to read. The trouble is, it stinks for availability, because if you have to write to all for be able to do a write, then what happens is if there's one site that's down, you can't do anything. Notice that, for example, when you work with n equals 5 and R and W both 3, even if one site is down, you can do reads and writes fine. You're only working with 4 instead of working with 5. But you can do reads and writes just fine as long as you can get to 3. It may be a little slower if a copy near you is no longer available, but you can still do everything that you did before the site went down. And there is this notion of mean time between failure, MTBF, which is, you know, try to have a situation where failures typically don't happen too often statistically. But there's also this MTTR, mean time to repair. Because, you know, if you had 5 copies and you want to have 5 copies and one of the copies goes down, you can bring up a new copy. It's work to get it to be a member of the other group and to get relatively current data so it can start, you know, participating with everybody else and really be able to help out. But you can bring up a new version of the data. And now you'll have 5 again. So if something fails, you want to bring it up because you still want to be able to survive failures. So you want to go back to having 5 and bring up another site and do it quickly. And especially when the sizes of the data, typically your partition pieces of the size of the data isn't that huge, and play this game so that bringing up another copy is not going to be that expensive. And by the way, the notion of size has changed a lot over time. Things that used to be regarded as big before and took a long time no longer are that big anymore and don't take as much time to question.
Does blockchain have any application in this synchronous replication?
Blockchain is a very, very interesting topic, and issues about how you do replication with blockchain are related to what we're talking about here. You don't typically use blockchain as a technique for doing this. You do this as a technique relative to blockchain.
Okay.
It's the other direction. So there is a variation because you can play a game where you almost always only have to read one site. And so you play a game where there is a site that you call the majority. So let's again say that we have 5 sites. And you need to write 3, and you need to be able to read 3, but there's a trick using the primary. You ensure that you always write the primary first. And then you write 2 more. And if you're doing that, as long as the primary doesn't fail, you can just read from one, namely the primary, because you're only writing to the primary. And you're always making sure that as long as the primary is up, the primary is one of the sites that you write to. Okay, in fact, you could write in parallel to the primary and 2 others, as long as your write is guaranteed to succeed as long as the primary is up. And so basically, by using the primary plus 2 more, that gives you your 3. And what happens if the primary fails? Then the other sites have to work out who the new primary is if you're going to follow the same scheme, and get somebody else up to date so it has all the current data, which is a certain amount of work. Or until the new primary is elected, you can just fall back to using R plus W then greater than. You can do something where you read 3 out of the remaining 4 sites, and that'll work as well. So replication is a very, very interesting detailed area. It's probably worth a course in itself. Last thing I want to mention on this before I go on more, we'll say more about replication, but there are schemes. So just as serializability is wonderful and people don't do it, there are lots of schemes in which people don't bother dealing with R plus W greater than N. There's an important system that Amazon did called Dynamo, where you can work with R plus W greater than N to keep track of, let's say, the contents of your shopping carts. They'll often operate with R plus W not quite equaling N. And so there are cases where you might end up getting people getting surprised by, their shopping carts have an extra item in it, or they reduce the quantity from 3 to 2 or something like that, and they end up being surprised about what's involved. And in their application, that's not regarded as a big deal. People will see things and correct it, or they'll hold on to an extra item, or they'll complain. There's a term that I'm thinking of inventing called business consistency, which is basically you have the cost of the inconsistency which gets built into how you run your business application. So this is a weird thing to say, and of course where we've tried to be rigorous about a certain amount of stuff. But sometimes the better business decision is to make the mistake and deal with it. As long as A, the mistake doesn't happen that often, and B, the mistake doesn't have a big business cost. And so just as people are willing to go ahead and operate without serializability, sometimes they'll work with replication which does not fully guarantee one copy serializability. It doesn't guarantee it, as if all the copies are the same. Weird things can happen, and people end up coping with it and dealing with it, often in a business and application specific way. I hate to say that, it's simply true. Okay, so if you're doing synchronous replication, then you have to be able to make the changes in all your copies and get locks on all the different copies. So you will send a request if you're replicating. You need to lock things at all the different sites. And if you have a situation where if you're doing synchronous replication with 2 sites going on, then you have to get the locks at all sites, and basically you end up having a complicated thing where everybody has to be involved if you're following that kind of scheme. So again, asynchronous replication is often used, and there are trade-offs on consistency and performance, and again, I have references which I believe are good links to Google Spanner and F1, and I also mentioned Amazon Dynamo involved in doing this. And again, the trouble with synchronous replication, by the way, the obvious one I mentioned last time, is if your backup has to have the copy before the active can do it, and you only have 2 copies, that's terrible availability. If your backup fails, you can't do a bloody thing. That's not high availability of any sort. So if your active fails, then the backup's going to end up having a problem because it doesn't have its partner around. And if the backup fails, the active can't do anything. So again, there are all sorts of variations that end up being used. And I'll say something about an Amazon approach as part of a coda in this. Let's see, so basically with the asynchronous, you have to be able to deal with approaches. For example, you could have a primary site and the primary sends to the backup, and again, you take the cost in case a backup, the last backup the primary site had, ends up not necessarily having been received by the backup. That ends up being complicated and expensive. There also is a peer-to-peer approach. Oh, this one is really interesting. It's sometimes referred to as multi-master. The idea is instead of having the primary being the master and the other site being a backup unless it has to take over, you can do updates at multiple sites. The trouble is the updates may end up competing with each other. 2 different people could have been given the last book. One guy changed the value of something, from the bank account from 20 to 50, and another changed it from 20 to 10. Which one applies, or how do you end up putting the things together? There have been a lot of different papers and a lot of different approaches dealing with it. I will tell you right now, it is a pain. But there are games that get played, including in a blockchain environment, sometimes where you end up playing a game of last updater wins, which means that if somebody has a lost update, you have to cope with that. Again, this is a long, detailed topic that would take at least a full lecture to discuss. Some of the approaches are, very sound. Some of them are hacks. And again, I will come back to this notion, a term that I've invented recently called business consistency, which is that you always want to run your business, you want to make things work, and you're willing to cope, and you have techniques for coping with things in case you end up having issues that exist. So again, in the peer-to-peer and the active, if you end up having 2 actives that can make changes, you end up having a conflict. So it's best used when the conflicts end up not arising. So you have a site where you have multiple masters and each owns a different fragment. So you partition the data into two pieces and each one of them ends up being fully mastered on the own. That ends up working nicely, but in fact, in practice, people really do use multi-master and deal with the consequences, even though, again, weird things can end up happening. If you end up designating one copy as the primary site, then that means, again, the primary site gets updated and then the other sites get updated based on the primary sites. So the other sites may end up getting may subscribe to things. So it could be something where the primary site ends up getting, all the updates, and maybe other sites don't have all of the data, but they only have the parts of the data that they're interested in. So, for example, you might subscribe to tweets by Justin Bieber. I don't know why. I think of other people to mention, but that gets too controversial. You got married recently, or whatever, or maybe you didn't. I don't know. I guess that was a Jonas brother who married Sansa. Anyway, you may be interested in. What can I tell you? I don't necessarily keep up on this perfectly. Sophia Turner, anyway, details. You end up subscribing to things that you care about. Obviously, I don't care enough about this stuff to really get it right. And just get told on that, and maybe you're in a read-only mode where you end up just getting the updates that are involved. So, how do you take the changes in the primary copy and propagate them to the secondary copy? There are two phases to this. One of them is to capture the changes that are made by commits at the primary, and then apply those changes at the other site. And I'm going to say a little bit about that, but I will emphasize that the details of this will not be things that will be on the final. So I'll give you two ways of doing this, one of which is better and the other is easier. The better way, and one which is used in an environment in which you have homogeneous replication, meaning it's the same data management system on both sides. So we'll deal with the primary and one of the other sites that's receiving changes, is you ship the log, or you ship the portion of the log that the other site cares about. Why are you shipping the log? The log has all the redo information. And if what you're doing is you're constantly shipping the new sections of the log to the other site, it can catch up by just applying the log records, by doing continuous redo as the log records end up reaching it. Redo does everything that the database transactions did. And of course, if a transaction rolled back, then the transaction rolled back, you undo it. So you're keeping up to speed with the log by just shipping the log and only applying the transactions that committed. Right? So that is a great way of being able to do it. So when you're writing part of the log to the disk, you're also shipping it to the other site. Not as a transaction, but you're guaranteeing that it will be done, and so you're getting things to the other site. Another earlier approach that was done, which still can be done and still can be a reasonable way of doing things, if you have a situation where you have sites that aren't homogeneous, where you have, let's say, SQL Server, Microsoft SQL Server at one site and MySQL at another site, is to go ahead and have pre-triggers that capture the changes that are going on. And the trigger says, when that change occurs, I'm going to send something to the other site, or I'll put something in a file for sending it to the other site. And I'll give you a third approach, which is a combination of the two. There are lots of different variations of this. Suppose that you have a heterogeneous environment. What you can do is capture the log, and then because it's another environment, you can't do redo with the log, but if you can figure out what the log means, people don't publish the details of their logs, but you can figure them out. It's work. It's particularly work when they change the log formats. But what you can do is, instead of applying the log, a redo record basically will correspond to an insert, update, and delete. You understand the log record, you can just apply the insert, update, and delete at the other site. So you're not doing a redo, but what you're doing is the operation that the redo would have done. And of course, you're going to have to undo appropriately if transactions roll back. So log-based capture is better, but it relies on proprietary log details, the trigger approach, which originally everybody did the trigger approach, Oracle and Sybase. Tandem and IBM did the log-based approach, which is better. Typically, again, people will go with the log-based approach when it's a homogeneous environment. Get the idea? You can just continuously redo. So you're catching up, even though you aren't the original site, but you catch up the same way. And then there's the apply step. So we've captured, and this is also not on the final. So you've captured all the changes that were done by transactions, and you know what are committed, and you know what applied. And basically what you can do is you can go ahead and you can update the copy based on the changes. So you're shipping the log, you can continuously be applying the log as you receive it, or you can do it periodically, okay? And by the way, there's no reason why the replica has to be exactly the same format as the original site. Example, the primary site might be row-based, the replica might be column-based. If you're applying the operation, you have to translate things appropriately. You can translate the thing and apply it to the other site. You could have a situation in which the other site is a view, assuming it's an updatable view. You can have something which is also a view on the original relation, and you just see what you can do about updating the view instead. So again, there's no reason why the copies have to look exactly the same as the original. You just are applying the log to be able to keep the things up to date. We know that some views are hard to update, other views are relatively easy. So again, log-based capture and continuously applying keeps everything pretty close to up to date, but not perfectly. Procedural is more flexible and works well in the heterogeneous environment. And the nice thing, by the way, about the procedural is it's easier to apply things when you have the column-based versus the row-based. So if you have a totally different representation, the original was row-based, and you say, oh, this is an update statement changing, you know, the value of these columns from old value to new value, the procedural approach can end up being applied. I'll just do the update statement, and that'll work if I have a column-based representation instead of a row-based. So again, replication is a long, detailed, interesting topic, okay? So one of the things that people do with replication is, and this was very common in the past, it's still done, it's not as common as it used to be. There are two ways that you can deal with warehousing, or OLAP kind of approaches. One way is a warehouse, another way is dealing with a mediator, where the situation is I have 12 different databases, and I want to be able to have a lot of information where I have, these days people talk about data lakes, which are variations of that's not quite the same. You have a whole bunch of data from a whole bunch of different places that I want to be able to gather together. And here are the two approaches that I can use, which we talked about briefly in the OLAP section of 180. One approach is you bring all the data into this big warehouse or lake. I don't know if warehouses can swim, but maybe they can paddle canoes, I don't know. So you have this data lake or warehouse in which you have all the data, and the data comes in from all these different databases. And maybe it comes in synchronously, and maybe it can be asynchronous, and maybe the data from different sites is from different times, but that's generally regarded as okay. You try to have it relatively current in all the different places. So that's an instance of asynchronous replication. And again, you can say, I can do a query. If I have multiple versions, I can do a query where I might be able to look at the data as it existed at approximately 2 p.m. yesterday, assuming that I can map to what 2 p.m. yesterday was in each of the individual data sets that I end up getting. But there's also the mediator approach, which is basically have all these separate databases existing, and if I want to ask a query across all of them, I'll ask a query across all of them, and I'll have the values there. The disadvantage of that is that my OLAP queries will be going against the same database systems that are doing my OLTP situations. And I want to avoid locking if I'm doing OLAP, so I may be operating with snapshot isolation. Recall that with snapshot isolation, I don't have to have any locks. I don't have to have any locks because I've got my old version, I don't have to lock it. I do have to do copy on write, but I don't have to lock. And so the advantage of that is I don't have to copy the data and send it around. The disadvantage is that I have more work going on in the place where I'm doing my OLTP, and so there are trade-offs between the approaches, and both can end up being used. And now, also, again, not on the final, there's a lot of slides like this where I mentioned that I want to go over the topics, but I won't be asking you about that. There's an issue of dealing with locking for things across multiple sites. So if I end up having a situation where one site does all the locking, all the locks are sent to that one site, that's easy, except it stinks, because that site has to keep track of all the darn locks, including locks maybe for other sites. But it's an easy thing to do. It's also vulnerable to what happens when that site fails and you've lost all your locks, okay? Another possibility is that all the locking is done at the primary copy site for the logic, which means that you have to go ahead and access the locking site as well as the site where you're reading it. So remember, I said you could read in certain cases from other combinations of sites, but basically the primary copy is a very easy thing to be able to deal with for it. And then there's distributed locking where basically you lock where that copy ends up being stored, including at different replicas. And if you're writing an object, obviously you're going to have to lock all the sites to make sure that you don't end up having conflicts. And then that leads into, and you already know about deadlock detection, leads into the problem of distributed deadlock detection. Because basically each site is going to be maintaining its, remember the wait for graph? Your transactions are waiting for other transactions to release locks. So you have the objects that you're waiting for. And you can have global deadlocks existing even though there are no cycles at a local site. But you could have a situation in which T1 is waiting for T2. T2 has a write lock, T1 wants to read it, T1 can't read T2. And it's the reverse on site B. T1 has a write lock, T2 wants to read it. Neither of them can proceed, right? So globally, you have T1 and T2 in a deadly embrace, And so here are 3 examples of solutions, and I'll tell you which one tends to be used. One of them is you can just send all the graphs around to a place that figures out if there's a deadlock. Another thing is that you can have a hierarchy of graphs where locks end up getting promoted through the hierarchy, so you can figure out what's going on and work it out. The one that gets used in practice is again timeout. This ends up being painful. And I will add a coda to it right now. What also often ends up going on in practice is you don't operate with full consistency, and you don't worry about it. Things end up getting designed with this notion, a word that I made up, or a pair of words combined called business consistency, where you don't worry about certain things going wrong. And again, I wish I could give you a systematic way of dealing with it. All I can tell you is it's done. Question?
So, I'm confused about why you'd want so many sites when it seems like there's a bunch of headache if you have like 38 sites and they're all pretty much just copies.
Well, it's wonderful to scale up and be able to have everything at one site, except that means everything's going to that one site. And if your amount of data ends up being huge, then that ends up being a problem. Now, it's also very nice if you can go ahead and design things for scale out with embarrassing parallelism, where no transaction touches more than one site, right? So you have so much data that you can't keep it at one site, but then you design things so that transactions only end up writing to one site. And maybe they read from other sites, but you're willing to have the inconsistency that comes from something where you don't worry about read-write conflicts. You operate, let's say, with a snapshot isolation, and you end up being okay because you don't have to bother with read blocks because you just use the version of the other sites as of some time. So that would be a way of doing it. If you care about serializability, and as I've emphasized, it's wonderful, it's beautiful, it's terrific, and nobody uses it because it's too darn expensive. Then these are the ways that you end up attaining it. So bottom line is, it depends on what you care about. If you care about serializability, you have to deal with this, unless everything fits on one site. But if everything fits in one site, then you have to deal with what happens when that site fails and all the takeover and having to deal with takeover for an entire site. And again, you end up not scaling because you're dealing with so many transactions going into that one site. So there are wonderful trade-offs that get played with, because you try to go with scale out so that you don't end up falling over. Scale up is wonderful until you hit the knee in the curve, which is the cliff. Everything's wonderful. Wah, so far so good, as the man said as he fell past the 12th floor of the Empire State Building. There will be a reckoning, or a wreck. So the trade-off there is, how you end up playing. You want to be able to design for scale out. You want to be able to design for things where you have smaller services. You want to design for microservices, for lots of serious applications that are out there. There are some things where you have to have large systems, and you care about what's going on. You try to design so that, if you can split it up, then you work it nicely. You have things where you do things where you do a workflow rather than a transaction. I mentioned this already. You do A, then B, then C, and if it turns out C can't happen, then you do a different transaction that said, oh, I want to compensate for doing B because I couldn't end up finishing this off. Example, I go ahead and I reserve my car, I reserve my hotel, I can't get my plane, drop my hotel room, drop my car. And there are variations of it. Painful, complicated, ugly. I wish I could describe it systematically. I've tried. I've asked other people. It just ends up being used. The bumblebee flies even though you try to tell it not to. And again, it comes down to levels of business consistency, things for your applications. Okay, now there's recovery, okay? And if you end up having a situation, and again, circumstance, we're assuming you want to do a distributed transaction, meaning I don't want to do a workflow in what I'm talking about now, and I will be getting to two-phase commit, which you should not confuse with two-phase locking. They both have two phases, they're very different, and they have different purposes. So the idea here is I want to do this transaction among 3 sites. And I want my transaction to either commit at all the sites or roll back at all the sites. I want it to be atomic across these multiple sites. I don't want to do A and then B and then C. I want to say A, B, C all have to commit, or none of them. Okay. So basically, I want to make sure all this happens, and this is where we get a commit protocol. So the idea is that every site has its own log. And there's a commit protocol. And we're going to talk about how that commit protocol works. And it is referred to as two-phase commit or 2PC. Do not confuse this with two-phase locking or strict two-phase locking, very different beasties. They both have 2 phases, and so we'll see how all of this ends up working. So basically, you'll take a site, typically the site at which the transaction began, and you'll have that site, I'm the big boss of this transaction. So it's the big boss for that transaction. Different sites may be big bosses for different transactions. It's referred to as the coordinator for that transaction. The other sites are referred to as subordinates. By the way, this stuff is on the final. It doesn't say none on the final, it's on the final potentially. So, and I believe some stuff related to this was on last year's final. So you have a coordinator for a transaction, and it's going to be in charge of making sure that the transaction is atomic. And it's got a log, but all the subordinates, so A is the coordinator and B and C are subordinates. And so when a transaction wants to commit, you have a transaction, the application says I want to commit. Okay, the coordinator gets the message, this transaction wants to commit. Well, I'll be the boss of that. Let's see whether or not this commit can happen. So what happens is, what the coordinator is going to do is it will send what are called prepare message to the subordinates. So in this case, B and C will get prepare messages from A. What does the prepare message say? It basically means, what does it mean? It means, are you going to agree to delegate to me the decision as to whether or not to commit this transaction? Are you prepared, if I tell you to commit this transaction, to commit it? Will you guarantee that? Okay? So the coordinator, the subordinate, is going to write one of 2 things. If it's going to tell the coordinator, no, I'm not willing to commit this transaction, it'll go ahead and it'll send back a rollback response and write a rollback log record, okay? And if it is definitely going to be willing to commit the transaction when told to, if told to, it'll write a prepare. Just as we had before, the rollback message doesn't have to get forced to the log. The prepare message does. Okay, so it will force the prepare to the log and send back a, yes, I'm prepared. And forcing that to the log guarantees that it means that it hasn't committed the transaction yet, but it's delegated the decision to the big boss back there, A. The rollback doesn't have to be forced. And it will send back a no in the case of a rollback. Won't do it. I vote no, I veto. And it's a veto. If one subordinate votes no, the transaction is going to roll back. Can't happen without everybody involved. If C is okay and A is okay, and B votes no, fail. The transaction will get rolled back. But if the coordinator gets unanimous yes votes, and of course, if it's willing to commit the transaction too, but it didn't have to write a prepare record. It knows about itself. If everybody, including the coordinator, is willing to commit, the coordinator will now write a commit record, which again, as we mentioned, does have to get forced to the log before the transaction actually gets committed. And it will send a message to all the subordinates saying, you're committed. Ancient joke in ham and eggs, the hen is interested in the pig's committing. Once you get a commit message, you have to commit the transaction. If you get something which says you get a rollback message from the coordinator, then you're going to roll back the transaction. Only if every subordinate votes yes does the transaction get committed. And now the coordinator has an important obligation. It's got to tell all the subordinates that the transaction is committed. Well, what do the subordinates do when they get the message? They will roll back or commit the transaction just as they would if it was a purely local transaction. And they will also send an acknowledge message back to the coordinator. When the coordinator receives acknowledgements from all of its subordinates, it will write an end lock record, which basically says, I've seen my duty and I've done it. Now, a couple of different things to add to this. When the coordinator writes its commit record, inside that record, it has a list of all its subordinates. That commit record has the list of all subordinates because it has obligations to make sure that all of its subordinates find out that this transaction is committed, even if some of them are temporarily down. That's an obligation. You've got to go ahead and fulfill that obligation. Because notice what's happening. Once a subordinate has voted, yes, I'm prepared, it's not going to be able to release locks on anything that it locked in the transaction until it hears back, yay or nay, from the coordinator, commit or rollback from the coordinator. So the coordinator has an obligation to all of its subordinates, which it must fulfill, even if it fails, even if one of the subordinates fail. Kind of an interesting, nice protocol, more details to follow. So there were two rounds of transportation, back and forth between the coordinator and the subordinate. One is to get the vote, yay or nay on the prepare. Okay, and the second round is to say the transaction committed or it didn't.